And welcome back after tea. So this focus, there are some subsections to my presentation, but the main focus is on using model approaches to identify where migration might occur in the future. And if you got really sophisticated models, maybe even who might be migrating, like by age, sex, and other characteristics like labor force characteristics. There's a lot of speculation about how many people will be migrating in the future. This was an art project in New York City. There are numbers that have been come up with over the period from the early 1990s onwards that look at how many people might be impacted and might be displaced as a result of climate change. But for the most part, we have no idea where these numbers came from. So that's an issue. I will say that my colleagues who did the sea level rise work at least were careful to say this is assuming a static population. So they didn't project population, and it's using a certain definition of sea level rise, which is in that case pretty extreme. So just a word to the wise before we get too far into this. All models are basically wrong, okay? And prediction is difficult, especially when it concerns the future. So we don't have perfect visibility into what the future will bring in terms of climate mobility as much any more than we have perfect visibility into what will happen in the next election cycle in any country on the planet. So all models are wrong, but some are useful. This is a classic quote. None of them is going to perfectly, modeling obviously isn't always about projecting the future. So I want to be clear about that. But in this context, I'm talking about projections of the future. But it may be useful to model because you understand how the system works better. Planning is everything, but the plan is nothing. So when it comes to future projections, having a precise number should not be the goal. But again, understanding potential magnitudes and potential what-if scenarios could be useful. I led the organization of this early workshop with this guy, Francois Jamin, who's another leader in the field of climate mobility. And he works at he used to run, at least, I don't know if he still does, the Hugo Center for Environmental Migration at Liège. At that time, he was at Sciences Po. And David Rathel, the fellow I mentioned earlier, is on the left-hand side. There's a bunch of people, Michael Oppenheimer in the middle, who's one of the world-renowned climate scientists. And there are a bunch of other influential people in the room. Basically, the point was that we wanted to find out what the state of the art was in 2016 around climate migration modeling. In that time, only a few models existed. Some were agent-based, some system dynamic, and I'm going to describe some of those early modeling efforts in a moment. More recently, last year in September, we organized a workshop. My postdoc, again, Fabien Cotier, now associate research scientist, and a bunch of people at Princeton and Cornell jointly organized a workshop to better take stock of what we know now about climate mobility modeling, because there's a lot more efforts out there, and to begin to do some intercomparison work. So we set up something called 3MIP, which is the Mobility Model Intercomparison Project. And you can join it if you want to go to this URL. Again, all this is on the Google Drive, so you don't have to necessarily do this right now. But this is an effort to, you can read more about the effort on the website, but it's an effort to systematically compare models and also develop a kind of hackathon approach to modeling future mobility where everybody's provided with the same baseline data and then people apply their own specific tools. And it hopefully will be a useful exercise. Let's get some, we've already learned, in fact, one of the participants over tea break was just mentioning to me that a lot of colleagues in his physical science department use the term environmental vulnerabilities, just as we used it in that urbanization study I mentioned earlier this week. And, vulnerability is not really the word you'd want to use. You'd want to use environmental exposures, or you might want to use susceptibilities to different, climate-related things. So in the same way that we have language specific to vulnerability research, we'd want to know better what some of these terms mean. So prediction is to say or estimate that a specific thing will happen in the future or will be a consequence of something. That's the everyday parlance, right? But from a statistical standpoint, we know that it's a process for using correlations between variables to hypothesize about future events and outcomes. So we use even the term the predictand, right? The thing that we're trying to predict is a predictand. And when we're doing modeling, we're often trying to either estimate the likelihood of something happening in the past or predict its likelihood into the future as a result of a change in some variable that's an independent variable. Forecasting is predicting or estimating a future event or trend. Hindcasting is when you take data from the past or actual observed data, let's say in climate, and you use a model. So let's say you have observed data from 1970 to 2000. You use a model that's set at year 1970, and you use that model to project forward the future climate. And then you try to look at the difference between the two results. And if you have a highly correlated result, meaning your root mean square error is very low for the results out to 2000, you're likely to have a high confidence that that climate model is capturing the dynamics in the system that produce that climate output. Well, in the same way, you might want to hindcast mobility, and we'll see that we actually do that in one of our methods in a moment. I think I can keep going, hopefully. Projection for migration is an estimate or forecast on the basis of present trends or extrapolated data on factors known to affect migration. They are contingent on particular assumptions or scenarios that tend to be very uncertain. So we'll talk more about projections. A what-if scenario is generally used in sort of policy analysis where you say, if I think, you ready? Okay. So we can keep going. I need Intejar to touch this again. It just worked. This time I don't need your help. I think I'm getting the magic too. Ooh, okay. All right. So what if scenarios are basically around the question of what might happen if we change this policy or that policy, or if climate change goes, really high versus really low in terms of emissions and in terms of final temperatures. So those would be what if scenarios. And it also helps in understanding the model sensitivity to those changes. So that's another reason for doing those tests. So you could do like a closed borders test and say, we're going to close all the borders to the US. What would happen with climate migration from Central America, for instance? Uncertainty, a state of incomplete knowledge. We talked about uncertainty, but it's perennially an issue, and we just need to keep emphasizing it. And then the standardized measure of uncertainty is the probability. Why do we do modeling in the social sciences? It's basically modeling is about reduction and abstraction to represent processes of interest that take place in the social reality. So it's a tool for inference. Modeling is an exercise in formalism, can be both qualitative and quantitative. By formalism, I mean the desire to extract general principles about behavior and things from individual behavior displayed across large populations, okay? So we're not interested so much about what Rajul is doing or Rezan or, Vijay, but we're interested about the population at large, and that's what formalism represents. By modeling and climate mobility research, we generally refer to quantitative modeling, which involves describing relations among phenomena of interest in explicitly mathematical and statistical terms. Whoops, 2 bullets. Quantitative modeling is appealing as it allows us to describe a phenomena, explain its causes, and predict future phenomena. It can be a tool of theory building. So we talked about theory yesterday. Modeling itself can help to both, it will be supported by theory, and theory is a very important element in undergirding modeling, but it's also a way of testing whether theories actually work or not, and produce the results that you expect. And there's 2 different types: a data-driven model, which is generally the statistical inference type model that we'll talk about in a bit. Simulation-based models are simulating things into the future. From a policy perspective, we need future population data for planning purposes. Humanitarians are interested in how many people might be displaced in the future. Development actors are grappling with limits to adaptation, particularly in the area of rural livelihoods. Receiving countries want to know potentially the volume of migration going in their direction. And policymakers, again, want these what-if scenarios based on high and low impacts, population projections, open and closed borders, and other policy interventions. Because we live in a real world, we don't have an alternative world to run experiments. I mean, some people call them digital twins, right? Models. You've heard the term digital twin. The idea is that you can build computationally a model of how the world works in a computer environment, in simulation. So there are different scales that some modeling takes, so you can think about evacuation modeling. Someone was showing me data from Landscan, which is a group in the US that does population grids. They're actually funded by the Department of Energy and somewhat from the Department of Defense. And one of the things they're funded to do is figure out if a disaster occurs in a certain location, how quickly can you get people out of that? So that's a simulation or a model they would run to show where people are and how quickly they could get out of a location to safety. Refugee modeling is over larger time scales and spatial and temporal scales. Finally, migration modeling is out in this. We're going to focus a bit more in this particular quadrant, the longer term migration responses. For those who are interested, we're going to cover a number of different approaches very briefly and kind of telegraph some of the approaches that are out there. But those who are interested in the topic more in depth, in the same climate mobility section of Climate Frontiers in Climate, we curated a bunch of really good papers, excellent papers on the topic. So if you're interested in learning more about modeling, these are some good go-to sources for that. So an exposure model, this is my terminology. I'm not saying everybody in the world uses the same terminology, but using the exposure, vulnerability and adaptive capacity approach, well, exposure means you're in the area of hazard, right? So the one that I mentioned earlier about future population change or populations affected by sea level rise in the coastal zone, this is that work done again in a later iteration where they look at urban and rural populations they look at the number of people being affected by sea level rise. The presumption is that most of those people would have to leave, so that's what I call exposure. It's implying or you can infer from this that the folks that are in this kind of submerged area will likely have to leave that area. And I mentioned they've done a version 3 of what's called the Low Elevation Coastal Zone data set, LECZ data set, that's available from our NASA CDAC. That version 3 actually provides several different DEMs, digital elevation models, population models, and urbanization models, so you can get a sense of the uncertainties. This is another by Michael Oppenheimer, which looks at sea level rise and economic losses and also implied population changes. I reviewed this paper. I'm sorry, I didn't particularly like it, but it does illustrate. So it never got published to my knowledge, so I shouldn't be showing it probably. but because it had some fundamental flaws, so that's why I'm not showing the authors. But what it does illustrate is a way of looking at drought-induced migration based on the same kind of exposure model, and they had different emissions trajectories and different levels of migration out of drought-prone regions based on the models that they ran, with cumulative migration listed here in millions up to 200 million in drylands of the world by 2100. Agent-based models tend to be more bottom-up models, and who here has anyone had been exposed previously to ABMs, agent-based models? So ABMs basically are, I think, perhaps the best kind of model for migration modeling, but they also have some of the highest data requirements because you really need to be able to understand how individual population, individual members of a society will respond to certain climate responses. They can also be done at the household level, so it's not just individuals. But they're based, a lot of them, at least the early ones, were based on this theory of planned behavior, which suggested that people have the desire to move and then they act on that. The desire first and then they act on that desire. ABMs are used in many different, they're used in industrial processes, economic models of ABMs. But for migration modeling, basically it assumes agents interact with each other to produce nonlinear outcomes. Agents exhibit complex behavior such as learning and adaptation. So agents are not just individuals, they're linked in social networks and information is exchanged between them. ABMs need to be calibrated with empirical microdata, meaning survey or census data. And ABMs allow us to test theories about how people react to climate stressors. This is just an early example of work. I'll show you one in a second that's a more recent, maybe more sophisticated ABM. But the basic principle is that for each, was work done in Burkina Faso, so these are the regions of Burkina Faso. But for each individual, there's a probability associated with that individual of migrating in light of certain circumstances. So young males would typically migrate with greater frequency and higher probability in relation to certain stressors that may occur. There's also asset bases, so like the degree to which they have material assets at their disposal. And so from that, you can basically take the probability of an individual to migrate with a particular social network and asset base in light of exposure to certain stressors, in this case drought, and you can aggregate that up to the community level and keep running that model iteratively. And what you would see is over time, more and more people moving out of an area. So this is thousands of migrants leaving a region of Burkina Faso out to 2060. So that's ABMs, again, very theory rich. So if you know a lot about your population and their propensity to migrate given certain stimuli, you can hardwire that in a way into the model. And you can even have that change over time. So like the propensity to migrate in response to drought could change over time. Maybe if you assume a certain things like increases in education level or changes in irrigation or other things that might affect ability, the desire to move, the aspiration to move. This is the Midas model. I've worked some with Andrew Bell, who's the author of this piece. And basically, it's a much more sophisticated model. And the idea is that individual actors have access to bundles of resources from different locations. Sometimes those utilities or the resources they access may be in their local area, like they might have farms or they might have livestock. They might also have relatives in the city who send money back to them. And those utilities determine in part whether they choose to stay or go. And if they determine that they can get more utility by moving somewhere else, then they will. It's a very economic kind of ag-econ, I guess, approach to looking at these issues. And so they did an interesting study in Bangladesh And they found that actually, somewhat paradoxically, there would be more migration towards the coastal zone in Bangladesh as a result of increased utility in some areas, like maybe shrimp farming or things of that sort. Um, that said, I didn't really like that banner headline because they also project a fair amount of migration away from the coastal zone as well. This is how science communication works sometimes. You grab the seemingly most controversial part of your research, and then you put it in the title of your paper. And so it was a bit more of a mixed bag than they're describing in that headline. So system dynamic models, we did some of this the other day, right? It was kind of system dynamic, not quite. We didn't get to the point of creating a fully operational model with lines going between like the cause and effect lines, and whether, if something increases here, it decreases over here, et cetera. And I'll show you an example of that for Kenya in a moment. They're very useful for what-if scenarios. They can incorporate a wide range of data on the economy, natural resources, and climate perturbations. It's easy to communicate the causal mechanisms. So one beauty of system dynamics is you can sort of visually just see how things are linked to one another. Kumu is the tool that I mentioned earlier, and you can do it yourself. Kumu will help you develop the causal network loops. To do it computationally, you still need to use a computational tool for that. I wouldn't be surprised, though, if there aren't some simple system dynamic software packages out there that you could maybe even download for free. So this is an example from a colleague at IDMC, and they were looking at pastoralist livelihoods in the Horn of Africa. And what they were hypothesizing is these loops that would exist from high rainfall to high pasturage, meaning a lot of grass. Land access is important. Pasture rejuvenation is important, so you need to have some fallow periods. High pasture leads to high livestock. High livestock is basically good for cash generation. And then you might have other forms of cash from remittances, from cash assistance from the government and livestock markets. So this is the system that they modeled, and then they used a system dynamic modeling framework to actually go through it. I'll try to dig out the name of that model because, as I mentioned earlier, there's free packages, and I think this one might be a free package that you could use. So what I just described was a bunch of positive feedback loops. So those same positive feedback, if you have lack of rainfall, then in the same way, your livestock will die or diminish in number. You'll have less cash, and you may be forced into an IDP type situation over here. Probably by far the most common form of, when you're talking about, in this case, projecting future states, is just to take a basic regression equation, find your coefficients, and then say if migration in Mexico is sensitive to crop yields, and crop yields are sensitive to drought, if in the future we're going to have more drought and more declines in crop yields, we can project into the future that there will be more migration to the United States from Mexico. So that's just a simple example. And you can see the quote I pulled out here from that article. And it's essentially what we call ceteris paribus assumptions, meaning all other things being equal, what would happen if this relationship is extrapolated into the future. It was done by some other colleagues of mine at Columbia, and I think in a kind of, it got into, gee whiz, it got into science, but it's not exactly what I would call a really robust study. I mean, statistically it's robust, but I think it came in for a lot of criticism because basically they were saying, looking at these, again, projecting a relationship into the future and saying, based on our understanding of where people are coming from, if you increase the temperature by 2 degrees or 20, from a moderate 20-degree optimum, and you increase that temperature, holding everything constant, asylum applications by the end of the century are projected to increase by average 28%. So again, that's really headline grabbing, and suddenly policymakers say, oh my God, 28%. but I think there were enough holes in their argument that there was some pushback around that. I hope I didn't. No, I did skip one. So gravity models, I'm going to talk a lot more about that because that's the one that we've been working with most closely at Season. But the idea behind gravity is similar to Newton's laws of gravity, which is that populations are attracted to other locations based on as a function of their population size. So cities are larger, they're agglomerations, and they tend to attract populations from surrounding areas. And so this law has actually been pretty highly predictive. If you use a gravity model from the past and project it into the future, and then you look at actual trends in population in the present day, the gravity models do a pretty good job of anticipating where people are moving in a lot of countries. Obviously, the form of the movement and the form of the statistical relationship will vary depending on whether you're in India or the United States or France or some other country. But what we decided, and I'll talk about this more in depth in a moment, is that you could introduce environmental characteristics into this model and sort of either increase the propensity of people to move into certain areas or increase the push factor. So you could make some places more attractive, or you could make some places less inviting, and therefore people would be leaving those areas. I started working with a colleague, Mikhail Brzezinski at Luxembourg, and he's been working with something called a computable general equilibrium model. He's a rare economist that likes to work in pixels and spatial contexts. He actually said, I almost studied geography, but I chose economics instead. And he has developed a really cool CGE. So CGE is a complex mathematical model that simulates the entire global economy, allowing economists to analyze the impacts of policy changes or economic shocks across different countries and sectors. So basically, it models, typically or traditionally, CGEs modeled economic trade flows and kind of economic outcomes. What he did was he created a CGE that have different locations that vary by their GDP, sectoral mix, production technology. Then he had individuals by age, gender, and education levels, so different tiers of population. And then he had, and each of them had their own consumption profiles based on empirical data gathered from each country of the world. And then he had damage functions damages that basically affected employment, productivity, amenities, and wages in different sectors and their effects across the landscape. And then per neoclassical migration theory, mobility is a result of differential wage rates and the cost of moving between locations. So fundamentally, it's a pretty simple model, but it produces some useful results. This is an example of projected migration change in population for 2100 for the Caribbean region. We did this model globally, but we focus the results on the Caribbean region. And this report will be coming out very shortly. But what you can see is a lot of the low-lying areas and flood-prone areas and areas exposed to the hottest temperatures are the ones that are going to see some of the greatest out-migration. There are a lot of other modeling types, and I'm not going to be able to, I don't have time to go through all of them, but this is an example of some of the studies that are out there that have used, for instance, integrated assessment models. Some have used artificial neural networks. Someone asked about machine learning yesterday, and machine learning has been used in some of this work. So definitely there's a lot out there, and it's a growing field of work. In terms of the limitations of each of these approaches, the fundamental limitation of exposure models is it assumes that most people or everyone will leave if there's a certain level of exposure, whether it's floods, whether it's sea level rise, or drought. And so, you have to figure out what that threshold is for people moving, but it's very mechanistic. ABMs require a lot of historical data, need to be calibrated very carefully. They do capture behavior very well. System dynamics often are not done in a spatial context, although that's changing. Extrapolation models quickly have the problem that it's, ceteris paribus assumptions cannot be held, in all cases indefinitely. So things change. The world is changing, and we can't just say, oh, migration will be thus and so based on climate impacts, because education levels, income levels, all those things are changing. Gravity models focused really top down, so it's not a individually based model like an ABM, but you can use them at a global scale, and we'll see how they were used in groundswell. But they talk about the relative attractiveness of locations, but not so much about the behavior of individuals. And CGEs are based on Homo economicus and may miss various cultural factors, things that result in people being rooted in place. They don't want to move. It also misses aspirations and capabilities, just like the gravity model does. So these are two modeling efforts that we were involved in at Season, where we worked closely with the modelers. The modeler, I should say, his name is Brian Jones. So Brian Jones had already developed a model that was a global projection of population on, I think it was 15 arc minute grid. 15 arc minutes, 15. Yeah, I think it was 15 arc minutes resolution for the world, and or maybe it was 2.5 arc minutes. Apologies, I can't remember. And basically, he projected out population density according to the SSPs. We talked about the SSPs before. This is just one of the SSPs. This is the fossil fuel development scenario where the world is on steroids economically because we're just digging up and pumping out all the gas and all the oil from the earth, and we're burning it as quickly as we can to generate a lot of economic activity. So that's not a good scenario, and it shows where some of the population growth would occur under that. But I said to Brian, I actually reviewed his article, and I talked to him later confidentially, and I said, I like what you're doing, but can we really assume that people will be moving into some of these areas in the future? Won't it be likely that some of these areas will be increasingly uninhabitable, or at least less habitable than before? He said, yeah, I agree with you, but I don't have money to do that. So we went together. I had interactions with the World Bank, and let me just, so I'll just talk a little bit more. So I had interactions with the World Bank. I was at a meeting. I mentioned that there was a possibility of doing this kind of work, and they were very eager to try it out. The trick was that for Groundswell, the report that we developed, we were really doing a research project with a very strict deadline and with a client that wanted to have results like ASAP, and they wanted them, and that's not how science generally works. So it wasn't the most pleasant experience personally, I'll be honest, because we were under so much pressure to get a result for the client, the World Bank. And when the World Bank says, jump, you ask, how high should I jump, right? That's what the general response is. At least that was mine, because they were funding us. So what we did to modify the model was we take advantage of the observed correlation between the agglomeration effect quantified in the gravity model and urban and rural patterns of spatial population change. So the model already projects urban populations separately from rural populations. But for Groundswell, we incorporate changing environmental conditions, considering sectoral impact indicators from the ICIMIP project. ICIMIP is I'm going to say it once, I'm not going to say it again, Intersectoral Impact Model Intercomparison Project, run by PIC. It's the Potsdam Institute for Climate Impact Research in Germany. And we looked at two variables, crop yields and water stress, and then separately we included sea level rise in the coastal zone. For the ACMI, which is the Africa Climate Mobility Initiative, we also added ecosystem impacts, which would include things like pastoral lands. Not just croplands, but pastoral lands and forest areas, flood risk, and conflicts. And we hypothesize, and this is where I'll show you how we calibrate the model, that prediction error from the model It was due to missing variables which relate to these climate stressors. Let me just show you what I mean by that in a minute. The way the model works is basically it takes a 100-kilometer circle around any given pixel, and it computationally figures out the potential of that pixel to attract new people in the next time step. So you're in T1, like this pixel will have much lower potential than this pixel because it's in a rural small town, right? Whereas being in a bigger city, it has more potential to attract new people. So the population potential or attractiveness is calculated. It becomes a new raster layer, which is fed into this. And now you see, lo and behold, this urban area has suddenly grown a certain amount, okay? And it's done separately for urban and rural populations, and everything is constrained. It's done on a national basis, so we don't do it globally. We do it by country, and all the data are constrained to UN population estimates out to 2050. So we don't project a population that's much higher than what the UN projects. It has to be constrained to those numbers. So we added, the idea is then if you have a drought in this area, you're more likely to see the potential decline even further in this area, and it probably would affect people moving into this area. Let's just run this through then to show how we backed out the actual migration numbers. So we have these globally gridded data. This is just an example for the ACMI that I developed. And what we have, and this is an idealized case of an island country that in this case is 45 kilometers by 45 kilometers divided into 3 15-kilometer grid cells on a side. So it's basically nine grid cells. And we project future population based on only the shared socioeconomic pathways, depending if it's SSP1 or SSP5. You'll see the SSPs we use in a moment. And then we also project future population based on both the SSP and the climate impacts, the RCP. And the climate impacts, then you see a population where more people are moving to the southeast of this particular fictional island's country. And you can then subtract this one from this one, and you get this one. And the red areas would be areas where you're seeing increase in migration. In the blue areas would be areas where you're seeing increase out migration. So that's just a stylized way of showing how we do it. Let's just look at Senegal. So this is actual results for the ACMI for Senegal, a country in West Africa. And all the red pixels represent in migration, and all the blue pixels represent out migration based on this subtraction of the two scenarios, the climate versus the no climate scenario. And then what you can do is add up all the red pixels, because the red pixels and the blue pixels will do what? They cancel each other out. Remember, population conserving. We conserve the population. So if the population is the same in the future projection for both the climate and the non-climate scenario, if people move between pixels, then all you have to do is sum up all the positive pixels and you get a total migration. And this is how we produce these charts that basically show cumulative migration over time based on climate impacts in the country of Senegal. And we had 4 different scenarios, and I'll talk more about those scenarios in a moment. But the numbers are not, the numbers are not huge. We're talking about numbers that are between 2 to 5%, 4% of the population climate migrants by the end of by 2050. Here's the model approach. We have the development pathways. I mentioned the SSPs. For groundswell, we only use SSP 2 and 4. And then we had the greenhouse gas emission scenarios, which were run through process-based crop models, water models, hydrological models, and I'll talk a second about that. And these resulted in 3 scenarios: a pessimistic scenario, high emissions, bad development outcomes to a more climate friendly scenario, which is better emissions or lower emissions and still bad outcomes, and then a more inclusive development scenario. So what we see here is that we had to use the model outputs from the ICIMIT project. We had to pick GCMs that we would use. So there were a number of choices that we had to make, which are all documented in the documentation, about which models we're going to use. We chose these models, for instance, for crop simulation, which are different groups out there producing crop production models into the future. And ideally, we would have filled in every one of these matrices here with a model output. And then we would have used all of these to come up with a better assertion of the uncertainty in our estimates. But the reality, we were under, remember I told you we were under the gun. We had to do this in a certain time frame. So we could only choose 4 models, 4 model combinations, meaning combinations of water models with crop models, water model, crop model, water model, crop model. And those were the model combinations that we used. And the result, well, let me just show you first. This is an example of the projected future deviations from the long-term baseline in water availability for the Horn of Africa. One of the things I knew was a problem was they were projecting greater water availability in the Horn of Africa. Recent historical trends have suggested declines in water availability and increasing drought. There's a fundamental problem in the global climate models with this region. It has to do with how they model the Indian Ocean in the way it affects rainfall in the eastern, the Horn area. And so we mentioned that in the report that there's a problem there. For Mexico, though, I think the model is fairly accurate for water availability into the future. Red areas will see significant declines, up to like 75%, 80% changes in water availability in some areas like the Yucatan over here. These, again, are based on combinations of GCMs, global climate models, and different water models. And so these are the high emissions here, high emissions and low emissions. So basically India, which may be of interest to some of you, is likely to see increases in water availability under most future climate scenarios. It doesn't tell you if that water is going to come in one giant downpour once a year or if it's going to come in nice spread out even. All right, so I have to move along a little more quickly. Here's some projections of crop production. By the way, if we have to cut it at 1, what I'll do, and we don't, I'll just take questions after the break and when we come back together, okay? So I'm happy if we don't have time for questions now to take those questions later. These are the projections of crop production for the different regions. Again, you're probably most interested in India, and so there are definitely, under the high emission scenarios, more, and under certain models, definitely some negative impacts in certain parts of the country for future crop productivity. But by and large, the picture is maybe a little better than in some parts of Mexico, for instance, where you see fairly significant declines in crop production. Sea level rise was just modeled using a digital elevation model in the coastal zone. So there are some issues with these data, particularly in like the Sundarbans. You may know a lot about this already, but this SRTM, which was the best available data when we started this process, and we were using whatever we could get our hands on, captures canopy height, not just ground level. So when you get canopy height, you've got mangroves that are really high in some parts of the Sundarbans, and that immediately what you're capturing is not actual sea level or ground level, you're capturing the height of the canopy. So I see some nods, and I know that some of you have some experience with that. This is an example of population in like the area of Cote d'Ivoire near Abidjan. All right. I'm not going to go into this too much because there's a lot of boxes here, but the basic point is we're projecting future population in the case of groundswell, it's 10-year increments every 10 years. So we start in 2010 because that was our baseline, and we keep going to 2050 in 5 steps. But in ACMI, we use 5-year increments. So we again started in 2010. The reason was that we don't have 2020 census data for every country in the world yet, right? So we needed to start from a very solid baseline. So 2010, we go to 2050, but in 5-year increments. That's ACMI. What we do is we do it for urban and rural areas separately. And here we add in local characteristics that are related to changes in crop and water availability. And we also we use a spatial mass for sea level rise. So when certain areas are flooded in the future, we simply reduce the probability that you can migrate into that area. And then at the end, you get these changes in population distribution. We have, under climate and no climate scenarios, two different population grids, and we can subtract one from the other and get climate migrants. Here I'm just going to have to really telegraph some stuff. This is the calibration. This is how the model. Sorry, this is not calibration, but this is how the local characteristics are incorporated into the model of future, the gravity model for the future. That red box is all the environmental variables that I was mentioning. It's a weight on the potential of that local area based on the impact of climate variables. So to calibrate it briefly what we're saying is this is where that term hindcast will come in handy. So what we did is we took data from 1990 to 2000 and 2000 to 2010, and we had actual population grids and observations. Then we ran a gravity model from 1990 to 2000 and then from 2000 to 2010. And when we ran that gravity model, what you tend to get is a smooth population distribution like this, all right, where urban areas are here and rural areas are here. It tends to be very smooth. So we hypothesize that any differences in that smooth distribution of population might be partially explained by the environmental factors, the climate factors. And so we had, our models had past crop impacts from climate, and our models had past hydrological impacts from climate. And so we were able to use those to try to explain the difference here. It turned out they were somewhat explanatory for why people were not moving according to the way the gravity model would have them move. So just to say that there was a calibration process, but it's done at a very coarse, large-scale level. I think I've covered this already, basically the combination of climate only, and SSP only, and climate plus SSP climate versus no climate scenarios. This is what it looked like for Ethiopia. We had 4 different models, combinations. Remember that chart I showed you with the diagonal going down where we combined crop and water models? And so each of these model combinations represented different combinations of crop and water models. And then for each one, we'd run it. And in this case is the worst case scenario, the SSP4, RCP 8.5, the one that we want to avoid. And it shows where people might move into in the South Highlands and where people might move out of in the northern sort of Western Highlands. These are the summary results. If you've ever read in a newspaper that up to 220 million people might migrate by 2050, that's in fact coming from the Groundswell report. It covers these countries of the world. And so I will emphasize that the gravity model, one of the benefits is you can cover a very large area. It's scalable in a way that ABMs are typically not scalable. One of the things I find unfortunate talking about media reportage is that the media very rarely ever reported the lower bound, which is about 45 million people possibly moving as a result of climate change impacts. One other thing I'll just point out is that these bars represent, in this case, the pessimistic or worst case scenario, and this is the more climate friendly scenario. Boy, did I breathe a sigh of relief when the results came out that way, because it wasn't necessarily clear or certain that we would get those results. And it would have been a lot harder for a policy report to say, we're going to see a lot more migration under a climate friendly scenario where we reduce emissions, right? So this was a windfall for the World Bank because they could make the argument that we really need to reduce emissions in order to reduce the propensity to migrate. The sensitivity of climate factors are much higher in places like sub-Saharan Africa than some other parts of the world. These are some of the summary kind of results that we did where we stacked all three scenarios, meaning the three SSP RCP combinations on top of each other. And we said, if you're in the 10th percentile, most in migration or out migration, you get a 1. That's sort of the value that you get. And then you stack those up and you get 1, 2, or 3 scenarios which say the people are going to be moving into this area. So we could then basically say some areas, all three models, or basically all three runs in terms of climate, future climate, were predictive of people moving into those areas or people moving out. And in some cases, it was only 2 out of 3, so they got the lighter shade of blue or red. So I don't know, we don't have Asia here, so I won't be able to describe that in more detail. But we were able to do things like look at migration in and out of livelihood zones by doing some basic zonal statistics. So all of these below the bar ones for East Africa show that people are largely going to be moving out of rain-fed agricultural systems. We saw a lot of movement into pastoral and rangelands. Again, this was largely an artifact of the fact that for much of East Africa, the projections were for increased rainfall, especially in the Horn. I think there's some real doubts about whether that will happen, but we were able to sort of explain that in the results. I think I'm not going to talk much about ACMI. I'm just going to flash some results of the ACMI. I will say that the ACMI numbers for Africa run about the same, even though we changed a lot of the model inputs and we changed the resolution that we modeled in, and we had a lot of different new variables that we added. The numbers were largely consistent across the two modeling efforts. If you look at the ACMI, an upper bound of about 113 million in Africa, and under a pessimistic scenario, around 105 for groundswell. So with that, I'll just leave the pros and cons up on the screen, and I think I am at 1 o'clock exactly, so we can stop. Dr. Rahman, tell me what you would like to do. Should we stop now? Oh, we can still have some time because I lost a little time. Remember, I did lose some time there. So does anyone have any questions about any of the work that's been described? And it's okay. If you're tired and you don't want to ask any questions, that's fine too. Nope? Okay. Good. We can also take questions after the break. It might be good to just freshen up a little bit and get some food in our stomachs. Yes, you're nodding. All right. There's no need to push it, Dr. Rahman. You can also come up to me and talk to me during the lunch break. Yes, there is one. Oh, there is a question. Okay. Let me pass you the mic.
So I think there's a lot about these quantitative data analysis. What about qualitative data? How can we analyze the experiences of people through qualitative methods? Would you like to say anything on that, or any methods?
Yes, I admit that I've given not as much attention to qualitative research results like in my first presentation this morning. And right now, this was all about quantitative approaches, partly because I've been a bit more focused on that. I was actually supposed to go to Gambia and talk to migrants and talk to families that send migrants just before, just this in April. and our project was cut. So the Trump administration cut the funding that we had to go to to do the field work. I had spent so long getting all the approvals, everything together, everything was ready, and then a month before I got the notification that we wouldn't be able to go to the Gambia. So, whoa, you know, so the answer to your question is absolutely. There are a lot of useful approaches to studying climate mobility, going to the field, talking to people, conducting surveys. You'll hear right after this, after lunch, you're going to hear a study that we're conducting in India. And part of what my point of that study is, we have certain statistical relationships. Now we need to go to the field and actually ask people if that's what's really going on. So you've hit the nail on the head, and I just want to thank you for asking that question, but it's really important. Yeah. Okay, ethnographic research, yes. So all of you who are saying all this, you know, statistical approaches are great, but what about asking real people out in the field? Remember that one slide I had was about contextualization and how all these quantitative studies, one of the things they often lack, almost 50% of them lack, is any local contextualization. Like a lot of them, the authors point out, not a single migrant was ever asked a question. And so, again, it's partly a function of the fact that there are a lot of data now. There's right now, like there's this group in the US that collects all the census data in the microdata, IPUMS, IPUMS. You can download tons of data from IPUMS. They undoubtedly have a lot of data for India. And that's microdata, basically household level responses to survey questions. So IPUMS is a good source, but you can download those data, analyze them from, you know, from morning till evening, come up with statistical relationships, and still miss important things because you've not gone to the field to talk to real people. Thank you for bringing that up. I think we should break for lunch now.
We have no. We have